Hi, in this episode we're going to implement wireframe rendering of a mesh in Unity when you are using the Universal Render Pipeline, often shortened to URP. We'll start with the basic wireframe where we outline each triangle, then we'll make a slight modification so that you are only rendering the quads. Finally, I'll show you how to overlay the wireframe on top of existing materials. If you're still using the standard render pipeline, please check my existing tutorials. Let's get started. In this case, I'll just create a standard 3D project using the Universal Render Pipeline. Just like last time, I'm using the windmill from the K-Kit Medieval Builders Pack. There's a link for this in the description. I'll import the hex forest detail and the mill from the FBX files, but this should work equally well with whatever shape or objects you wish to apply this to. Feel free to just use a simple sphere or cube to start with if you like. I've dragged both objects into the hierarchy, which creates them at the origin. I'll just move up the mill so it sits on the tile. I've turned off the icon for the global volume as it's just getting in the way. Then we can select both objects and create an empty parent called windmill, and create a prefab out of that. Then I'm just duplicating this with Ctrl D and spreading them out. I've got 4 copies of the windmill, one for each of the effects we'll see. First, a recap of the process we're using in case you haven't seen my original videos. Let's think about how this works in reality. When you are rendering an image, you process each triangle in turn in the fragment shader. So let's consider a solitary triangle for now. Each vertex of the triangle has a coordinate in the world and a UV coordinate for the texture mapping. Let's assume the triangle is visible, then in our fragment shader, each pixel is going to be found by interpolating between the UV coordinates of each vertex and the texture to find the required pixel value. Can we use something similar for creating a wireframe effect? What we really want to do is colour in the pixels along the 3 edges in these areas and leave the centre transparent. We can use the Barycentric coordinate system to help us find out how close we are to an edge. The way this works is by assigning each vertex a value from 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then for any pixel in the triangle, we can interpolate between this coordinate system to find if we are close to an edge. So you can consider this as 3 axes that come out of the vertex and head towards the edge opposite, where the value is 1 at the vertex and 0 at the edge for each of the 3 coordinates. For example, this pixel would be 0.5, 0.5, 0.1. So given the pixel coordinate, we can say if any of the 3 components are within some threshold of the edge, then we'll colour that in, else we'll leave it transparent. This will effectively draw our wireframe for us. One consequence of this method is that you'll get double thickness lines for the lines where the triangles join, but single thickness at the edges. However, as most edges are internal to a mesh, this will not be very noticeable. Back in Unity, we'll create a base shader we'll work from. Right-click, create shader, unlit shader. I'll simply call this wireframe shader. Okay, so in our shader code, the first thing we want to do is add some extra properties. The first one will be the underscore wireframe color. In the brackets, the first thing is what the Unity inspector will say about this, and the second is the type. So for our wireframe color, we want this to be of type color, so we get a color picker, and we'll default it to an opaque white. The second one is underscore wireframe scale, which will be a float, and will default to 1.5. This is the wireframe thickness, so to speak, but it's not in any real units that are intuitive, which is why I called it a scale rather than a width. We've got 2 more bits to add, but I'll come back to those in a moment. To the subshader tags, we'll want to ensure that this shader is in the transparent queue. So we add Q equals transparent. This is because we're going to use transparency to do the wireframe, with it solid at the triangle edges and transparent elsewhere. Along with the Q, you have to specify the blend mode when doing transparency. Here we'll do the standard blend mode of source alpha and 1- source alpha. If you aren't familiar with blend modes, I wouldn't worry about them at this stage. The first thing we want to do in the pass is to turn face culling off with cull off, and also turn off writing the depth information. We do this with Z-write off. You could equally turn off the Z-test, but not writing the Z-depth information has the same effect. The reason for this is that normally the shaders optimize away all the faces you'll not see, but as we're doing a wireframe, we want to make sure that every line is visible. We'll have to revisit this later when we want to draw the wireframe over an object's existing materials, but for now we're fine. We're going to be using the geometry shader to add our barycentric coordinates to do the wireframe. In the rendering pipeline, this sits between the vertex and the fragment shader. The stock shader doesn't have the function for this, so we need to tell it what we're going to call it. So add a new hash pragma line for the geometry shader called geom. We'll add this in a second. Whilst we're here in the parameters, we'll add two more things we'll use to help with all our wireframe variants. We're adding these with hash pragma shader underscore feature. This tells Unity to compile different versions of this shader depending on what the material has chosen. This way, we get one shader to do different things without having to have branching in here, which is bad. The first one will be the wireframe draw type, which we will prefix this with underscore wireframe, and have three options, which are basic, fixed width, and anti-aliasing. We'll also add one underscore quads on to enable the quad versus triangle wireframe. So that Unity understands what the options for these are in the properties section, we can let it know. Our underscore wireframe option is of type keyword enum, and we just list the three options. These keywords will get appended to the end of the underscore wireframe to make the full name. Our underscore quads will be a toggle, and the toggle type automatically appends underscore on or underscore off depending on if you select it. Great, that's it for our setup. Let's dive into the code proper. Now that we are going to add a geometry shader, we need to include the structure that holds the data, much like the v2f struct we have for the output of the vertex shader. I probably should have named the v2f struct here to v2g, as it's now vertex2geometry, but I forgot when writing the code, sorry. So define our new output struct for the geometry shader as g to f. This is going to have two things in it. The first is a float for, which is the position. I've called this pos because that's what I did in my last series, but most other geometry shader documentation you see would probably continue to name this vertex. For the G2F geometry struct, in addition to the position, we'll add an extra float 3 barycentric. This is going to hold our basis vector for each vertex. We assign this to text coord 0 because you have to assign it to something, and we'll fill it in the geometry function. Now the only thing I'm going to change in the vertex shader is rather than doing the Unity object to clip pos transformation on the vertex, I'm going to pass the vertex straight through. This is because we'll need the raw vertex information in the geometry shader later when we do the edge culling for quad wireframes. You could also move the transformation of the texture and fog to the geometry shader too, but as we're doing the simple wireframe, this isn't necessary, and I've just kept the shader changes to a minimum. Now let's add the geometry shader. The first thing that's different about this is that we prefix it with a max vertex count with a value of 3. This is so the shader knows how many vertices you'll be adding in each call. Since we're just processing triangles and not adding any new points or anything, it'll just be 3. The input to the function is a triangle, which is defined as 3 vertices in the in array. Then, as the geometry shader is actually a void function, it has an in-out parameter where the results will go, which is the triangle stream. Okay, so to the actual code. I'm going to include at the start a float3 modifier, which you just set to the 0 vector. We don't need this right now, but we'll use this when we do the quad wireframe, so it's just easier to include it now and we'll update it later. Create a new G2F object called O. We don't need 3, one for each vertex, we can just keep reusing this one. So we just want to create the vertex position in the pos variable as we would normally. To do this, we call Unity object to clip pos, which, if you remember, we removed from the vertex shader, and apply this to our first vertex in the in array. Then we have the new data. We want to add our barycentric float 3. we are going to set one of the parts of the float to 1 for each vertex, so we'll just take them in the order, and for the first one, set the first value to 1 and the others to 0. We'll also add on our modifier here. As it's 0, it's doing nothing at the moment, but we'll come back to that. Now the struct has the vertex position and the barycentric data, we can append this object to our triangle stream. That's the first one done. We do exactly the same with the other 2 vertices in the triangle. Each time we make sure to update the position of the 1 in the barycentric float 3. Okay, so that's all the data we now need, which is passed to the fragment shader. So let's jump there and update it. I've removed everything from the fragment shader, as we'll start fresh here. Note that I've updated the input I to a G to F from the original V to F. So that we can use our variables inside the pass, we have to declare them here. So we'll add the fixed 4 wireframe color and the float wireframe scale. Depending on the type of wireframe we're producing, we'll need to do different things. So here we'll use the hashif with our parameter of underscore wireframe basic for this first iteration. The if block is closed with the hash endif. So this bit of code will only be included in the compile shader if we've selected the parameter basic from our material, which we'll see later. This isn't a dynamic if statement that gets executed at runtime. The fragment shader operates on each pixel. What we want to do is render our wireframe color if we're close to the edge or transparent if not. The fragment shader is doing all the magic interpolation of our barycentric values for us based on the values we assign to the vertices. We know that the barycentric coordinate value on the edge is 0 for one of the components, so we can just take the minimum of our 3 components to find out how close to the edge we are. Create a new float called closest, and this will be the min of i.barycentric.x against the min of the y and z components of the barycentric coordinate. As the barycentric coordinates at the vertices are a maximum of 1, this will be a value between 0 and 1. In fact, it'll never be 1 because you can't be at all 3 vertices unless the triangle is actually just a point. So to set the alpha value, we want it to be opaque if the closest value is less than, say, underscore wireframe scale divided by 20. This threshold will mean that if you have your wireframe scale set to 1, then the wireframe line will map to about 5% of the triangle's size. We do this with the step function. This is simply 1 if the first parameter is smaller than the second and 0 otherwise. This is one of those nice GPU functions that saves you having to do an if statement. Then we can return a fixed 4, which is our pixel color, as the R, G, and B components of wireframe color, and our calculated alpha value. So it will be opaque, colored at the edge, and transparent in the middle, which is what we want. Let's jump back into Unity and check that out. Okay, so the first thing we need to do is convert our shader into a material we can use. Right-click on the shader, create material. This will create a material for us with the shader applied. Let's call this basic wireframe. You can see in the inspector we have the correct shader at the top and our color, scale, rendering type, and quads only options added. Not that half of them do anything yet, but it's set to basic, which is what we've implemented, so that's good. Now we can simply drag the new material onto each part of the windmill. I'm doing this in the scene, or you could do it in the inspector when you select the model. If you watch my original wireframe video, the swapping of materials like this between the opaque and the wireframe was how I did the building animation effect. You can see that's working, but you've probably guessed it's a bit basic. That light reflection on the tile is making it a bit hard to see, so let me just quickly turn that down. On the directional light, we can select emission and lower the intensity to about 0.1. That looks good. We can still see the shadows, but it's easy to see what we're doing with the wireframe in this bright scene. Because the wireframe is drawn as a proportion of each triangle, the larger triangles have bigger wireframe lines than the smaller ones, which looks very messy. The small details on the accessories of the tile look good, but the windmill looks clunky in comparison. I can turn the scale down to 1 and it looks a bit better, but clearly the thinner lines look so much nicer. But the good news is we're 90% of the way there, and we can see the start of our wireframe. Let's jump back into the shader code and make the fixed width wireframe. To get a constant width line, you need to know how big the triangle is in some way. To do this, we want to know the rate of change of our barycentric value as we move through the pixels in the triangle. HLSL has two base functions that do this for you, ddx and ddy. These calculate the difference between two pixels in each of the horizontal x and vertical y directions. To combine them, we can just sum the absolute values of them. This is something that comes up a lot, and there's a nice helper function to do this for us. This is exactly what the fwidth function does. With this fwidth function, we get essentially a standardized unit of change for the given triangle. So in our fragment shader, we'll create a new elif block for our _wireframe_fixed width. Here, the first thing we do is get the unit width, which is a float 3 using fwidth of our barycentric value for this pixel. This value will be bigger for little triangles, as for every pixel you move, you've moved across more of the triangle, and smaller for larger ones. But the important bit is, if we colour in some multiple of the unit width as our wireframe, the absolute size will be the same no matter which triangle it is. This is exactly what we want. We have to switch things around. We can't first get the closest point and step on that. Instead, we have to do the step function first. This is because the unit width can be different in the x, y, and z coordinates. So we'll define a new float 3 called edge to be the step of the barycentric coordinates against the unit width times wireframe scale. This means the coordinate of the edge will be 1 if the barycentric value is less than our adjusted threshold. So to put it another way, it's 1 if it's an edge. Then for our float alpha, we can simply set this to the maximum of the x, y, and z coordinates of our edge. Again, using two max calls to work over the three variables. If it isn't an edge, all three will be 0, thus alpha is 0 and it will be transparent. If 1, 2, or 3 say it's an edge, then alpha is 1 and we'll draw an edge. Let's jump back into Unity and check that out. Let's create another material from our shader. This time we'll call it fixed width wireframe. In this material, we can update the rendering type to fixed width. Then we can drag this on to our second windmill. We can already see this is looking so much better. All the lines are the same width. However, what you can probably see, assuming the video encoding hasn't blurred it out, is that lines are jagged. For each pixel, there's a hard transition between wireframe and transparent. So we need to jump back into the shader and add one last variant, the anti-aliased one. In our fragment shader, let's add the third and final elif block for the _wireframe_anti-aliasing parameter. For this, we'll calculate the unit width as before with fwidth, but this time, rather than using step, which just goes 0 to 1, we'll use the smooth step function to output into our float 3 aliased. This is slightly different as you need three parameters. The first is the minimum, which will be the 0 vector. The second is the maximum, which is our unit width times wireframe scale. And the third is our value for comparison, which is the barycentric vector. How this function works is that the output is 0 if the value is less than the first, 1 if it's greater than the second, and smoothly interpolated between 0 and 1 in between. Remember, barycentric is 0 at the edge, so the alias value is going to be 0 at the edges. This is the flip of the last one, just to confuse us. So to create the alpha value here, we take the min, so we get the smallest, and then we need to do 1 minus this value to invert it, as we want the edges which are 0 to map to an alpha of 1. Hopefully that makes sense. Let's jump back into Unity again. For our third windmill, we'll once again create a material from our shader. This time we'll call it aliased wireframe and select the anti-aliasing rendering type. Then we can drag it onto our windmill once again. This looks a lot better. Again, not sure how well this will come through on video. So let's zoom into the sails a bit. You can see these internal triangles look really smooth. And if I bump up the wireframe scale parameter, that should be really obvious. If you look closely, you will still see the edges are jagged. This is because we're smoothing away from the edge where we have an adjacent triangle, so you get the smoothing in both directions, but at the edges you don't. This is not an easy thing to fix, but it's a small fraction of the edges, so hopefully that will be okay with you. If I have the fixed width one next to the aliased one, you can clearly see the difference. The aliased one looks much nicer. Giving the smoothing, the aliased one will have thinner lines, so you may want to up the scale a bit if you want. Often when you see wireframes, they can look a bit cluttered with triangles. It just feels like there's too many lines. So the next extension is to make this shader only render quads by removing some of these lines. For a quad, we're just considering two triangles next to each other. We'll start by looking at a square. In our fragment shaders, we're processing all the triangles at once, harnessing the power of the GPU. But this means that we're operating on each individually, so we aren't able to query about the adjacent triangles. So if possible, we want a method that will work when considering the triangles in isolation. The key observation to make here is that in this case, and indeed most simple model cases, the edge we want to omit from our triangle is in fact the longest one. As you'll remember, we rendered the line for each triangle, so internal edges will be constructed with 2 lines and the externals with 1. Our longest line removal property is true for both of the triangles in this case, so that works out nicely. However, on some meshes like this triangulation of an octagon, that isn't always true. For the rectangle in the center, the longest edge is correct for both triangles, so we can correctly remove that. On the segments at the top or the bottom, this isn't true for both triangles. In the topmost triangle, the longest edge, highlighted in yellow, is the one you'd naturally want to remove, so that's all good. However, the other triangle's longest edge is the one that's also part of the rectangle, highlighted in red. So if we remove the longest edge, we'll take 1/2 of each of these lines. The result is that we'll still end up with triangles, though with our aliasing only on one side, so they'll both look a little thinner. To improve this, you'd have to do lots of pre-processing of the mesh to pair up triangles to quads, but we're after just a simple shader. So I think this is an acceptable compromise. We won't remove the leading diagonal from all quads, but at least the chances of us incorrectly removing a whole edge is very low. Going back to our triangle with barycentric coordinates, how do we achieve this effect? We render the line when, for our pixel, one of the values is close to 0, and that means it's close to the edge. So we want to ensure it's never true for our chosen edge. The barycentric coordinate is interpolated between each value seen at the vertex. So if we add in the barycentric base vector for the vertex that controls our longest edge to all the others like this, then that coordinate gets interpolated between 1 and 1. This means that it will always be 1, never getting close enough to 0 to be rendered in our wireframe code. So back in our code, the only place we need to make a change is in the geometry shader. If you remember, we had the float3 modifier, which I said we'd come back to. This is what we're going to populate now. If we make the modifier be the barycentric parameter we're interested in, say 001, then when we add that on at the bottom, we'll get our doubled up ones to stop things being rendered. The eagle-eyed among you will notice that for the vertex's edge we want to suppress, this means we'll actually end up with a 2 there rather than a 1. This actually doesn't matter. We'll now be interpolating between 2 and 1, so it still has the effect we want of never being close to 0, thus never rendering the line. So how are we going to do this? Firstly, we only want this code to operate when we have the show only quads option selected in our material. So add a #if _quads on to detect this and end with #endif. Again, this means that we'll only compile the bit of code if necessary. To find the longest edge, we first must construct the edge lengths. Remember, we want the length of the edge associated with the barycentric coordinate. This is the one opposite. So for the first barycentric coordinate, we need the distance between the other 2 points, 1 and 2. The distance function does exactly what it says. Then we do the same for the other 2 vertices. Then we just need to set the modifier based on which is longest. We have to use some if statements here. So if edge length 0 is greater than edge length 1, and also edge length 0 is greater than edge length 2, then this is the longest edge, and we set the barymetric modifier to match the barymetric vector 0 as 1, 0, 0. Then we check if vector 1 has the longest associated edge, and then the last one. That's it. All the other code works as before. Back to Unity again. I'm running out of windmills. Turns out I'll need one more. Let me quickly duplicate this one so I have one for later. Okay, create another material from our shader. This time we'll call it quad wireframe. On this one, we'll check the quads only boolean, and I'll use the anti-aliasing render type. Then we can apply this to our fourth windmill. That's the best looking one yet, I think. You can see that as expected, not every triangle has been reduced to a quad, but it's pretty good. The last thing to do is quads over the model's original materials. If we're going to be having the wireframe render over the object's existing materials, we need to make one slight change to our existing shader. But we can't do this as a parameter, so we'll have to copy it. So copy and paste our wireframe shader, and we'll call this new one front only wireframe shader. Within the shader itself, there are only two changes we need to make compared to the original one. First, set the shader name at the top to be unlit/front only wireframe shader to match our file name. Then, in the pass before, we had cull off and Z write off, so that every wireframe edge would be drawn. In our front only shader, we can remove both of these and add cull back. This does exactly what it implies, and it removes all the back facing triangles. With Z write off removed, we'll also be depth testing, so triangles behind our foremost faces will also be removed. We can't make this a parameter and control it with an if like we did before, because the callback is before the CG program starts. So we can't have any code there to do any logic. Back in Unity, we can right click on our new shader and create a new material from it. I've called this front wireframe, and I'll set it to anti-aliased quads using our parameters. If you have a single submesh, you can simply add this to the materials list and it just works. Our windmill has multiple submeshes and materials, so we'll come back to that in a moment. I'll quickly add a coloured sphere to the scene and just move it out of the way. In the inspector, you'll see under the mesh renderer section, you have a list of materials. We currently have one element, which is the lit material. We can click on the plus icon to add another element to the list. To this, we drag on our front-only wireframe. And just like that, it's working. You can see the wireframe rendered over the top of the sphere's existing material. Amazing! You'll see the warning stating that the renderer has more materials than submeshes, so multiple materials will be applied to the same submesh. Well, guess what? That's exactly what we wanted, so that's all good. Let's get rid of that sphere now. It's more likely your object, like our windmill, has a bunch of submeshes with different materials assigned to them. You can see here we've got 5 elements in our list. In this case, if we do the same thing, clicking on the plus, then dragging in the wireframe into the new slot, then unfortunately the wireframe is only added to the last submesh. Only the grain sacks are looking amazing and have the wireframe on them, but the rest of the object is left wanting. Instead, we're going to have to use the render features of URP to achieve this. Let's remove that extra element now. We're going to apply our wireframe over the existing objects based on what layer they are in. So let's add a new layer in now. I'm a bit tired, so in the empty slot I called this windmill. I probably should have named it wireframe. Now, for our windmill object, let's change the layer to windmill. And if the object has multiple children, you'll get a pop-up asking if you want this on all of them. I'll say yes in this case. In Unity 6, which I'm using, the URP renderer is located in the settings folder. Here, select PC renderer. Obviously, you'll have to do the same for mobile renderer if you want this to work there also. At the bottom, click Add Renderer Feature and choose Render Objects. If we expand this out, you can see there's a bunch of settings. The event is when you want to do this extra rendering step. The default is after rendering opaques, which is what we want in this case. This means the render action is going to happen after the object has been rendered, but before any post-processing is done. If you open it up, you'll see there's a variety of options you can choose from depending on when you need your extra material effect to apply. As we're rendering the wireframe over the object, I'm assuming you've got an opaque object, so we can leave this in the opaque queue. If you have transparency on your model, then you'll need to change the event and the queue to the transparent variants. This render objects pass will happen to anything in the same layer, so we select the layer mask to be our new windmill layer. Anything in the windmill layer will have this effect. In the override section, mine is already expanded, you can choose what we want to do. The override mode is material, which is what we want, and we can just drag on our front-only wireframe material. And just like that, we've got the wireframe rendering on our windmill just like we want. Doesn't that look great? It's also rendering on the hex base, which I don't want, but that's easy to fix. I can just go to the base and move it back to the default layer, and the wireframe is gone from it. It's that simple. Just as before, you can change the settings on the material if you want and see the changes. And that's it. Hopefully you're now able to apply the various wireframe shaders to all your URP objects. I hope you found this tutorial useful in some way. As ever, the full code is on GitHub and linked in the description below. See you next time.